Hello, everyone. The title of my message today is about vectors. And as I mentioned in my previous video, a student asked me to do a video on vectors. So this is going to be a part one of a series of, we're going to go very deep actually into vectors. We're going to start out with vectors in two dimensions. And I was thinking today, actually, when I was preparing the lesson, I was thinking about how vectors, in a sense, blend precision with timeless principles. Vectors offer not just a lesson in math, but really a reminder. One of the reasons I like them so much is because they really are a reminder of the enduring value of order, clarity, and balance. And as you think of the word endurance, endurance is a mark of good character. How well any of us endure adverse circumstances, financial reverses, a difficult work environment. How many of you have heard nowadays, you hear so many quitters? So many people just quit. Oh, I have a bad boss. Oh, I can't stand so and so as a coworker, and they quit. How well a married couple endures the strains and inevitable difficulties that are found in any marriage relationship. How many people do you know they quit their marriage or they quit their relationship because of one disagreement? How well you have situations in the churches, how well somebody endures the bad circumstances that sometimes exist even in good churches. And yes, how well you endure your math lessons. A lot of people just bolt. They don't endure the good or the right when it becomes a trouble thing. They just, you sort of take the coward's way out and they leave. That's not a mark of a good character. And part of the reason why so many students, by the way, aside from the fact that it's true that their educational system can be very poor, one of the reasons why a lot of students are failing in math and another subject is due to the fact it has to do with the lack of endurance. You will not, listen, now hear me out here. You will not become a successful mathematician unless you actually have some kind of endurance. And even if you didn't want to become a mathematician, you will not do well and you will not be successful in your math unless you apply a consistent principle of discipline, study habits, and yes, understanding the rules that are there. So I hope that this is going to be part one of the video. I hope this is helpful to you. This was just kind of an introduction, and let's get to it. Hello, everyone. So we're going to talk about vectors today. And as you can see on the board, a vector in two dimensions is it's an ordered pair of numbers, and they are often written as this, right? You have a parentheses, you have x and y. They are called, the x and the y are called components of the vector. Think of it kind of like as a well-mannered duo. The x and y are the dynamic duo, each with their own role to play. And if you bring them together, then they form the components of the vector. It's a concept really very much grounded in logic and structure. And yes, we believe in structure around here. The first thing we're going to talk about is the operations, right? So vectors have two operations. Well, the following operations, we could call them addition, and we add the vectors by adding the corresponding components, right? Just as individuals tend to be stronger when they work in harmony, vectors often combine their efforts and they produce something greater together. So if you were to add them, let's say you had AB and you wanted to add C and D, well, now you have A plus C and B plus D. All right? So that's the first thing. Then you have something called multiplication of a vector by a constant. So when you multiply a vector by a constant, you multiply each component of the vector by the constant, right? Now, typically constants they're labeled as k. So let's say you had the constant being multiplied by a or b. Now you would have ka and of course kb, right? And usually, typically, we put these in parentheses as well. All right? Now, we often refer to real numbers as scalars. So if you have this in your notes, scalars. That's spelled scalars when we speak of vectors. So the product, this k parentheses ab, we commonly refer to it as a scalar multiplication. Later on, we'll see why real numbers, why they earned this name when speaking of vectors. So instead of referring to a vector by the components, you can actually give a vector a label. And when you do so, typically, we use a bold lowercase letter that is not italicized. You'll see the V a lot. Other notations other notations sometimes that are used to denote a vector can be V with an arrow. Actually, I should write this down since you're probably taking notes. So V is one way to label the vector. And sometimes you'll see, like I said, you'll see a little arrow over it or a little caret symbol. We'll talk about that in a moment. So when you're representing a vector geometrically as an arrow, right? Like if I were to I did a little diagram actually so that you can see it visually on the coordinate plane. And let's see if it shows up. All right, there you go. So you see here, we have an arrow, and that's being represented. If you look at the arrow from 0, 0 to 1, 3, that represents the vector 1, 3, right? And you also have an arrow that goes from 2, -4, and it goes all the way to 3 and then -1, right? So those are arrows that represent the same vector. And now the location of the vector is irrelevant. So any arrow that depicts right one unit, up 3 units would represent the vector 1, 3, right? And again, if you're labeling it, you would just write parentheses 1, 3. All right? So occasionally we refer to vectors with points, right? Like as you can see on the bottom here, BC, that's for the vector that is represented by, it's the arrow going from B to C. If you write a vector with 1 point, as you see here with A, then you just do a little arrow there above the A. So that means that the vector is coming from the origin to that point, right? It starts at the origin and it goes up to that point. Now notice that the notation BC, if I were to write it as like this, it's going to be a little bit, notice I put the arrow be kind of like not covering it all the way. That's slightly different from a notation if I said BC. If I told you like BC like this, that's actually talking about the ray that starts at point B and passes through C. And it keeps going forever in that direction. So the vector is the little arrow there. You could represent it by an arrow. It goes from B to C, but it stops there. Now, we won't always be this precise in our language when referring to vectors when you're dealing with a geometric context. We often just simply we just say an arrow that represents a vector, or simply a vector, right? We're not going to litter the text with saying an arrow that represents, an arrow that represents. So if you let V equals 1, 3, all right? If you let you can see there that both A, right, the little with the arrow and the little arrow over BC are actually representing V. And so you can write A equals BC equals V basically. All right. Now a vector, if the vector has a magnitude of 1, it's actually called the unit vector, right? So the vector can be written, right? So let me write that down for you all. A vector with a magnitude of 1 is called a unit vector. All right. So you can write xy, you can write it as xi plus yj, and I would be the unit vector. All right. The unit vector. Right? And if you're going to label the unit vector, you would write it as parentheses 1, 0. And j would be the unit vector 0, 1. All right? So that you have I is 1, 0. You have 0, 1 there. All right? So for example, the vectors, let's go back to the diagram. This right here. So the vectors A and BC are both I plus 3j. Now we'll mostly use the notation parentheses 1, 3, but occasionally mix in with the I plus 3j notation, just so that you can get comfortable with it because it does come up quite a bit. Right? So when you're naming vectors, we have something of a touch of formalities. And just as I said, we typically label them with lowercase letters. Clarity matters, right? And the location of the arrow doesn't change the vector. What really matters in a vector is actually the direction and the magnitude that matter. It's really a principle that resonates deeply because truth and values remain constants, no matter where they're placed, much like in real other contexts of life. Um, and then, of course, you can think of the unit vectors as sort of the standard bearers, right? It represents that when you have a magnitude of 1, well, it's really representing the ideal. Um, so much like in life, different forms can coexist without compromising the essence. Now you have something called the zero vector, and the zero vector is when both components are 0. All right. So we typically denote this as just simply 0. And we also have a special symbol for the set of all vectors in 2 dimensions. And that is represented by R, open R, like it looks like the real number symbol, right? So we're going to say R squared, right? So the R squared is representing the set of all vectors in 2 dimensions. You recall how I've talked about this many times, how it's so important to know what set of numbers you are dealing with. And why do we use this symbol? Well, remember that this symbol represents the R, represents the set of all real numbers. So we use the R squared to indicate that we're talking about the set of all ordered pairs of real numbers. All right? So this when you have it's really a nod to the infinite possibilities within, very important, within a structured system. right? After all, much like in other contexts, right? Like it's just like when you have freedom, freedom thrives best within boundaries, right? So if we blend this precision with timeless principles, the vectors, you'll see vectors offer it's not just a lesson in math, but it's really a reminder of the enduring value of order, clarity, and balance. So we're going to solve a couple of problems here that I've created for you. And I hope my color scheme is attractive. I hope it works. Let's see if I can pull it in. All right. So this is very important. We define the norm of a vector xy to be the distance xy to the origin in the Cartesian plane. Right? We denote the norm of a vector v is, those two lines and then v. So we're going to find xy in terms of the norm, in terms of x and y. Right? So I want you to take a moment, pause, and see how if you're familiar with vectors, how you would do this. All right. Did you pause the video? All right. So what you do here is you have to apply the distance formula. Right? So if we apply the distance formula, we would have this. Hopefully I can use red. And we have to take the square root, so we have to subtract x minus 0 squared plus y minus 0 squared. And all of that, of course, we're going to take the square root. And I mean, x minus 0 is x, and you have an exponent outside the parentheses, so it's x squared. Y minus 0 is y, and you have a square, so it's going to be the square root of x squared plus y squared. Very important. Please put this somewhere visible in your notes. Okay, so the norm, NORM, of a vector is defined in this way. We're going to call it V. The norm of V is x squared plus y squared. Now, you can also refer to this as the magnitude or length of the vector, because again, it measures the length of the geometric representation of the vector. So that's very important. All right, so that's our derivation. Now, I'm going to give you a couple more problems, several more problems actually, so that we can see if we can solve them and we can expand on the logic. If I go too fast, you can always pause the video, right? And you can. All right. So I have 4 problems here. The first one says if V equals 3i plus 4j, then what is this, right? So let's try those problems, put a pause on the video, and then we're going to solve them. All right, so the first one for A, we're looking for the norm. So the norm of V is going to be equal to, we just derived the formula. We have 3 and negative 4. So we're going to take the square root of 3 squared plus negative 4 squared. Square root of that. This gives me 3 squared is 9 plus negative 4, right? That's going to give me this 16, right? So we have 9 and 16, which gives us the square root of 25, which gives us 5, right? So that means that V if we were to solve this, we now have 1 over 5v and that's going to be equal to, now we have 3i minus 4j, so now we have the 3/5 I minus 4/5 j. All right. So once we have this, we're going to take, like I said, we have to use the formula that we had earlier. And so we're going to take 3/5 squared plus negative 4/5 squared. And of course, we have to take the square root of that. And if you break it down, you're going to actually get 1. All right? Let me know in the comments section if you have any questions about this problem. All right, now let's look at the second the second problem. It says 7 and negative 7. So we again use the formula. We have the norm and we're going to do 7 squared plus negative 7 squared. Square root. And we get, if we simplify this, we have 49 plus negative 7 squared is 49. So it's going to simplify to the 7 times the square root of 2. All right. Now, that means that we're looking for v over v. And we now have, so that's going to be 1 radical 2 and negative 1 radical 2. So that means that now we have 1 over 2 plus 1 over 2, square root of 1/2 plus 1/2. And that gives us 1/2 plus 1/2 is 1. So that gives us 1. Very suspicious. Right? Let's look at the third one. 0.5 and negative 0.2. Right? Let's see what happens here. Well, if we use our formula, we have 0.5 squared plus negative 0.2 squared. And of course, we have to take the square root of that. And see what you come up with from that. All right, that should be giving you, if you pause the video, it should be giving you the square root of 0.29. 0.29. Now, if we use our formula, right, we have 0.5 over radical 0.29. And we also have negative 0.2 over the same square root. Now, rather than rationalizing the denominator, right? Remember, when you have a radical in the denominator, you have to typically rationalize the denominator. So rather than doing that or getting rid of the decimals, we can forge ahead. And because at this point, you should be pretty confident, I hope, that something convenient is going to happen. If you take these two values and you square them, you're going to get, if you take the 0.5 over radical 0.29 and you square it, you're going to get 0.25. And if you take the other number, negative 0.2, and you square that, you're going to get 0.04. And now you have 0.25 plus 0.04 using the same formula divided by 0.29 square root of 0.29, and then this, right? So now you have this, and that actually simplifies to 1. To avoid confusion, we're going to get rid of this but we're going to get 1. Very convenient indeed. Now, at this point for D, I think you should be pretty sure of what's going to happen. You have a pretty good idea what the result will be. If you work out the details, you're going to get 1, right? Because V cannot be equal to 0, of course, right? It's a non-zero number. So as you noted in your other problems, and as we mentioned earlier, when you have a vector that has a magnitude of 1, that's just called the unit vector. And when you divide a non-zero vector by the magnitude, you get a unit vector, right? I hope this is pretty much clear. So geometrically speaking, you can think of the unit vector that as providing the direction of the vector, and the magnitude as telling you how far the vector goes in that direction. So since each non-zero vector, since you can write it as the product of its magnitude in a unit vector, you can literally think of a non-zero vector as being defined by the magnitude and its direction. And you can also define the direction of the vector by using an angle. We're going to see that in the next problem that we're going to do. All right. So let's do, I have to write it out probably because, all right, we're going to let xi plus yj, we're going to say that it's a non-zero vector. And we're going to let okay, and we're going to let r theta, the angle, where r is greater than 0, be the polar coordinates of the point with rectangular coordinates. Actually, I'm going to try and put in my original part because I have the good symbols in there. I don't want it to be sloppy. Let's see if it lets me put it in. All right, this was the problem that I was able to. All right, there we go. How are r and theta related to the vector xi plus yj? Now, the solution to this, we want to know how r and theta are related to the vector xi plus yj. So we have x equals r times the cosine of theta. By the way, this is a pre-calculus course, right? So if you're watching this, I'm assuming certain prerequisites of knowledge. I just want to throw that out there in case. So we can say x equals, and of course y equals r sine of theta. So let's put in those definitions. So x is equal to r cosine theta and y is equal to, you're going to have the r times the sine of theta. And what happens is we're looking for xi plus yj. So r cosine theta is going to equal the following. Let's see if I can show you in a neater way the solution. Okay, hopefully you can see it on the screen. So we have r cosine theta times of the I part plus r sine theta j, right? And then we have x squared plus y squared. And r is the magnitude, as we talked about. We talked about the magnitude of something because of this justification. Cosine of theta plus sine of theta is equal to cosine theta squared plus sine theta squared equals 1. So you see that cosine of theta plus sine of theta j is a unit vector. So theta can be used to describe the direction of the vector, right? So hopefully this makes sense, right? I wanted to also show you, we're going to let v be a non-zero vector. And if that's the case, how are v and 3v related? Geometrically speaking, of course. All right? So take a moment to think about that. And then I'm going to show you a diagram. All right? So hopefully the diagram you can see. So what can we do here? You can let v be AB, right? And you have 3v here, which is in the 3a and 3b, right? So the origin, where is the origin here? We have the origin that goes to the point AB and the point 3AB, 3b. Those are called collinear, collinear. Why are they collinear? They all lie on the line through the origin that has the slope b over a. And of course, a is non-zero. Because if a is equal to 0, then all the 3 points are on the axis, on the y-axis, just to be clear. So if we can look at this diagram, I hope you can see it well, but notice how v and 3v have the same direction. So if you want to be more precise, you can express each as the product of the magnitude and the direction, right? So you have, if you were to plug it in to an equation, you have, and that's going to be 3a squared, right? And well, we should say actually 3b, right? Because if we have v as a squared plus b squared, this is kind of like our our starting point, right? So that means 3v has to be 3 times this, right? So it's going to be 3 times your a squared b squared. All right. And if that's the case, right, you have v is equal to, if we're looking for the relationship between v and 3v, right? So what is the relationship that you can see here? You should be telling me that 3v has the same direction as v, but if you notice, right, it has 3 times the magnitude. So 3v is a scaled, what we call a scaled version of v. And if you want to see it worked out, I was able to put it in a neat way so that you can kind of have this in your notes. Right? And this is the reason that we have. Right? Now, related to this question, right, if you go back to the graph, we're going to let negative v equal negative 1 times v for any v. So how are v and negative v related? Right? So let's see if I can put in a diagram again. All right? So we're going to let negative v equal negative 1 times v. For any v, right? So how are they related? Well, if v is equal to ab, then that means negative v is negative a negative b. All right? So look at the two vectors in the diagram. You notice that point AB and then you have point negative A, negative B. They're on the line through the origin. They go through the origin, and of course, again, the slope is B over A. And again, A cannot be 0 because if A equals 0, then all the 3 points on the y-axis with the origin in the middle. But the origin is between here, AB and negative A, negative B. So the origin is equidistant, equal distance from AB and negative A, negative B. So you see that V and negative B, they have the same magnitude, but the opposite direction. All right? So hopefully this video, this first part, because this is only a first part, at least has introduced you to a preliminary notion of what vectors are. In the next video, we're going to be doing more problems. And also we're going to be talking about, so this is kind of like what is a vector. And then we're going to be talking about dot products in the next video and possibly lines and linear dependence. We also have to talk about projections, right? So there's a lot more to say, but hopefully this was a good starting point. Thank you for watching.